All right, everybody, here we go. We're going to talk about the intermediate value theorem and some consequences that follow. I'll refer to the intermediate value theorem as the IVT. So here we go. Let's just start by talking about what it is. If you think of the equation x cubed equals 6, think about it. We love it. I'd like you to think about how you could just quickly, using technology, solve for x. So think about it. Maybe pause the video and use your calculator to solve for x. Welcome back. Hopefully you paused it. The question is, how many different ways could you find it? I can think of 4 different ways. And so if you want to pause again and think about how you could find x in a variety of ways, go for it. If not, I'm going to jump into it right now. Way number 1. You could take x cubed equals 6 and take the cube root of 6, and that'll give you a value of x. There's a cube root button in there. You could also do x cubed equals 6, and if you think about taking the 1/3 power of both sides, 6 to the 1/3, you could plug in, and that'll give you another value for x. Remember too that the cube root is the same as x to the 1/3, so maybe the same, maybe different, depending on how you interpret it. Another way that may take a little bit longer is a graphical approach. If you think about the graph x cubed, and then you think about the graph of just 6. When you have x cubed equals 6, it's literally saying where are they going to be equal. And so whatever value of x, that would also be a solution. You could, come on, dude. You could also take x cubed and subtract 6 from both sides. And then if you graphed that, meaning take your x cubed, shift it down 6 units, so it looks something like this. Wherever that's equal to 0, that's going to be the same x value that was found over here. So if you find the value of x using your calculator, any of these 4 ways, you're only going to get an approximate. That's the best we can do. The IVT is a property of continuous functions, right? That's what we talked about earlier this week, that guarantees there is an exact value. So this is the first of these type of proofs. It doesn't necessarily give you the value, but it guarantees that it exists. So that word that we've talked about a little bit, that does a limit exist? It doesn't necessarily give you the value, but it tells you that it's there. So here it is more formally. The intermediate value theorem. If a function f is continuous for all x on the closed interval, a to b, and y is a number between f of a and f of b, there is a number, x equals c, in the interval a to b for which f of c equals y. What a mouthful. So I'm going to try to draw a picture to represent this, because that can be a lot. So here is just some arbitrary graph. And the first line says that the function f is continuous. So I'm just going to draw some function that I'm going to call f. And it says that it's continuous for all x values, that's this axis, on the interval a to b. So let's just make up an interval. We'll say this is a and this is b. So if you think about it on the graph, this value right here would be f of a, and this value right here would be f of b. So on the closed interval a to b, closed just means that those endpoints are included, and y is a number between f of a and f of b. So y is somewhere in here. So the conclusion says there is a number, x equals c, for which f of c equals y. So what this IVT says is that there's some value, and because it's continuous, there is some value where f of c equals y. And hopefully you can see that on the graph. So there's my visual for the IVT. All right, let's do an example and kind of see it in action. Let f of x equals x cubed minus 2x squared plus 3x plus 7. So it's a cubic. Find approximately a value of f of, x is c, between -1 and 2 where the output is equal to 5. Prove that there is a value there. All right, so we have to kind of interpret this using the notation. So we're going to graph part of this in a second, but the first thing it says is we want to find a value between -1 and 2. So that's actually giving us our interval. So when we talk about our interval a to b, you know, a in this instance is -1 and b is 2. So we really care about this interval. And so I'm going to look at the endpoints there. I know that at 0, the intercept is 7, so we can fill that in if we want. 2, 3, 4, 5, 6, 7. So I know it's going to pass through there. And if I want to find f of -1, we can substitute, you know, -1 in this cubic. I'm going to do it by hand, but you could also use, you know, technology. Maybe make a table or something. So we got -1 minus 2 minus, you know, 3 plus 7. I think you're going to get a 1. So that point would be like right here. So that would be your f of a value. Right? Because a is the beginning of the interval. And if you do the same thing for f of 2, I'll let you pause it if you want to, but you can trust me, it's going to be 13. And so f of 2 is going to be up here, way up here somewhere at 13. Now, this is a very crude graph. Hopefully you know that a cubic, you know, has kind of this shape to it. But the point here that brings this IVT together is that we know that if the function is continuous, there's not going to be any holes or gaps or issues. And so I'm going to change colors here, but I know if I'm starting here and getting to here, it's going to have some curve. Again, my graph's not drawn accurately, but it is continuous. And 5 is right here. And so if it's got to start here and end here, right, and I can't lift up my pencil, then at some point it's going to pass through 5. Right? It's got to cross that threshold at 5. And I can see visually that it totally does. Now my graph's not that great, but I would guess that it passes through, you know, somewhere on the negative side. But again, my graph's not that great. Actually, it has to pass negative because the intercept is 6, so it's going to pass through on the negative side. So I would say x is approximately negative point something. I'll leave you to find that. You know, I highly encourage your graphing calculator or Desmos, and you can use a couple of the strategies graphically that I talked about here on the first slide. But we care about the IVT, so we really care, does it exist? And so what would that proof look like if we were to write it up? Well, it looks something like this. It says since f of x is a polynomial, right, x cubed, x squared, those are all polynomials, it is continuous. And remember, continuous is part of the if statement. And since we found the endpoints, you know, this was our f of a, this is our f of b, to be 1 and 13. The number 5 is between 1 and 13. You could also think of it as, you know, 5 is between 1 and 13. So if you like inequalities, you can think of this as, you know, f of a. You could think of this as your y. You could think of this as your f of b. So this is saying that y falls between f of a and f of b. So the other hypothesis, the if part of the IVT, is true. So what am I referring to? I'm referring to, it says, if the function is continuous, it is because it's a polynomial. And if y, that was our 5, is a number between 1 and 13. So I'm basically taking the theorem and translating it with actual numbers. So it is between 1 and 13. Therefore, there is a number x equals c And if you found it, again, it's approximately negative point something. Between negative 1 and 2, why does that say 2? Yes, because of my x value, sorry. There is a x between negative 1 and 2, and that decimal would fall between there, for which f of c is 5 exactly. You're not going to have to do a lot of proofs in this class. One, because there's no proofs on the national exam. But the most important thing about this IVT is that you can follow the notation. The notation is a heavy part of this class, and usually at the end of the year, when I get feedback from students and talk about the challenges for the year, reading the problems, interpreting what was being asked, understanding the notation, that's usually one of the things that is a challenge. So try to get on top of it early. Thanks for watching. Good luck, and I'll see you soon.